So let me be very clear, now that we're recording. Yes, correct. I don't know what an adjective is. I don't know what a verb is. I don't know what an adverb is. I know a noun. Proper noun is a person, place, or a thing. Boom, I got that down. We're good to go. Okay? What? I literally have 1 out of 5 or 6 or 7 or whatever. Okay? But here's the problem. Is that quiz easy? That quiz that says name 3 adjectives. No. Is that quiz easy? Yes. No. For some of you, yes. That's it. Could you easily get 100%? Yes. For some of you, you could easily get 100%. Mark, before I forget, return the chair back when you're done with it. Okay. But is that quiz hard for some people? If you don't know what the hell an adjective is that quiz going to be hard? Yeah, it's going to be impossible. Just like today's quiz. If your quiz today says something, something, something isomer, and you don't know what an isomer is, are you going to be very successful at that? No. That's the trade-off with organic chemistry. The trade-off is there's very, very, very little math. When's the last time you used a calculator? Your last unit exam. You have not needed one since then. And you will not need one. You will not need one for the remainder of organic chemistry. There's literally no math involved at all. But what's the trade-off? If there's no math and no problem solving using numbers, then obviously, well, now we're switching into the domain of words, terms, and vocabulary. So there is vocabulary in organic chemistry that is critically important to your understanding. That's why we talked about words that come before words, otherwise known as a prefix. That's why we've talked about words that you attach to the end of a word, a suffix, right? Remember, are we always going to use "een"? No, it depends on the context if there are double bonds present, right? Are we always going to use "oct"? No, it depends on the number of carbons that are involved in the main chain. But that all has to do with vocabulary, right? There's a big trade-off in organic chemistry. It's some people love organic chemistry because there's no math involved at all, and it's all very much conceptual problem solving. It's, do you understand the procedure? Do you understand the focus of what we're doing? And then you just solve it. You don't need a calculator, right? But with enthalpy and energy, probably every second question, or 2 out of every 3 questions, was a number or problem solving question, right? So it's just, that's the trade-off we get. Before I forget, sorry, I've altered this a couple times, right? You're not going to have 2 double bonds. Don't worry about it. I was just trying to show people that was a possibility. It's all good. It's okay. I printed off the equilibrium unit review and the organic chemistry unit review. And so I'm giving you the equilibrium unit review right now, as well as the organic chemistry unit review. Hey, how many people grabbed these already from this row? So we only need 4. Yes. Yeah, it's the reason why it's so thick is because it's. Yeah, okay. I tried to hole punch this, but when you burn through this many sheets of paper, the hole punch compartment of the printer gets filled up pretty quickly, and if it gets filled up, it doesn't just magically stop printing and say please take out please empty the hole punch with waste. It just keeps printing, and I'm not going to hole punch these for you. I printed them off for you, but I'm not going to hole punch them for you. Okay? You can do that later. You can do it 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 later, Preston. You can do it later. later, Preston. You can do it later. Okay, here's the organic review. I literally don't know if it's going on. I literally don't know if it's going on. Hey, most of the organic chemistry booklets are hole punched. A couple of them aren't.
Yeah, that's not the whole one.
Here. Ow! I don't. Yeah.
I was like, I know that. I know
Hey, can you put your names on both of those? Just like straight out of the gate, please. Can you put your names on these? Why am I asking you to put your names on them? Because if you leave them in my class, then I know who to give them back to, right? That's what I would really appreciate that. Please. Thank you. Really appreciate it. Okay, why is this? Yeah, when I drew it back on there. Yeah. I appreciate it. When I drew it back on there, I just didn't. Cool. Okay, so now I've handed back the review booklets. That's 2 out of 4 that I printed off. How long did it? I'm not trying to ask for your sympathy. I just want to let you know how long it took me. An hour and a half last night. Just sitting there and waiting and jamming and unjamming and jamming and unjamming. And it's just the way it goes, right? Whatever.
You could have done so many things while you were waiting.
No, I couldn't have, because honestly, I had to wait for the printer to jam so that I could unjam. I had to just wait there for it to unjam. Maybe I'll bring your posters. I totally didn't count. No, I'm
save it for the mark them tonight. Save it for the break.
no, because I don't want to bring the posters. Okay, let me know if I didn't give it up. Did I get the exact? The worst. Just comes back right.
Well, yeah, that makes sense. Don't worry
Hey, if anybody wasn't here yesterday, remember I handed out the schedule, the study schedule. And I also handed out the major assignments, right? So those are there. Okay. We're going to go through, we're going to add a little tiny bit more. We're going to add a little tiny itty bitty bit more to your naming repertoire. And so, yeah, we're going to talk about the organic halides. So another way of saying this, the organic halides are also known as the alkyl halides, or like a halogenated hydrocarbon. They all mean the same thing. Halide, halogenated, halogen, they're all mean the same thing. Okay, what are we talking about here? Halogens. What group on the periodic table? 17. Yeah, that's okay. No, I know. Somebody else did. Yeah. So it's group 17, right? Column number 17 or family 17 on the periodic table. So let's go through them. What's the first one in group 17? Fluorine, chlorine, bromine, iodine. Astatine is radioactive, so it doesn't really technically exist, but that's fine, whatever. So we are going to just over off to the side. You should have a little bit of room in the margin of your page. When you have an F group, we call that a fluoro group. Whoa. They all end in O. So what do you think Cl is going to be? Fluoro. Yeah, good.
Okay, that was on the
A
assignment.
fluoro group. What is a BR?
Bromo.
Bromo. And this one's the toughest one. Iodo. Good, yeah. So iodo, bromo, chloro, and fluoro. Okay, so the organic halides are compounds with a halogen functional group. This is the first time that we've added, now we're talking about elements that are not carbon and hydrogen. What that means is these are called functional groups. They function differently than other parts of the molecule. If I add an iodo group or a fluoro group or something like that, they will function. That part of the molecule is functionally different than the rest of the molecule. The rest of the molecule will behave a certain way, but this part will behave a very specific way. Is that okay? So now we're changing the behavior of the molecule. That's what a functional group does. It changes the behavior of the molecule. If I had pentane, and then I added a methyl group on here, does that radically change the behavior of this compound?
No.
No, it doesn't. That's not a functional group. It's a branch, right? That's just a methyl branch at carbon number 2. But this is changing the way the molecule reacts. It's going to behave differently under certain circumstances. Now, we name it the exact same way we name everything else, okay? Everything is still in alphabetical order. The double bonds are still the highest priority. Double and triple bonds are still the highest priority. So let's just go ahead and name this thing. Where are you going to start? Do you want to start at the beginning or the end of the name? We're going to start at the end of the name. So how many carbons in a row? 5. 1, 2, 3, 4, 5. And what do you notice? What's unique at the very end of this molecule? Ene. Where's it going to start?
1.
At carbon number 1. So I would put it here, right? I would go 1, 2, 3, 4, 5, and I would start it at carbon number 1. And then, so where are all of our functional groups and where are all of our branches?
1, 3, 3.
1, 3, 3. So what do we have at carbon number 1?
A dibromo.
We have one bromo. We have a single bromo at carbon number 1, correct? Because there's only one there. If it said 1, 1 dibromo, then they'd both be on number 1. So we have a bromo group attached to carbon number 1. What else do we have? Where else do we have bromines attached to? Carbon number 3. So I'll put it here. We got a bromine there. And then where's the methyl attached to? Number 3 as well. So that's CH3. And then we just fill in the hydrogens like we normally would, right? So how many hydrogens can go on the first carbon? 1. How many can go on the second carbon?
1. 2.
1. Why 1? Because it had a double and a single bond, so it's got 3 bonds already, right? How many carbons can go on, or how many hydrogen can go on the third carbon? None. 0. Zippo. Nada. Why? Zilch. Good. That's a good one. It already has 4 carbons, right? How many can go on the fourth? 2. And the last one? 3. Right. Terminal carbons, if they have no branches or anything, well, terminal carbons can't have branches, but if they have no functional groups, then they have to have 3 hydrogens. Yeah.
So all of these like alkyl halides, they all have a bonding capacity of 1?
Yes, all of the alkyl halides have a bonding capacity of 1. What a fantastic question. What the hell does she mean by that? Max?
It means there's only one lone pair on the electron ring, so it can only attach to one thing.
It's the other way. It means they only have one orbital that's not a lone pair.
Yeah.
So when you look at a bromo group, if we look at a normal bromine atom, if we're only talking about its valence shell, right? You could count all the way from left to right and see how many electrons are in its valence shell, but it doesn't matter. At the end of the day, only one electron is unpaired. So there's only one possible bond that it can form. Everything else, nah, whatever, it's already occupied. It's full. Full occupancy. Good? It's this, naming is like, no problem. Naming is just, it's just fluoros, bromos, chloros, and iodos. That's it. So let's go ahead and name these two compounds. We're going to name the one on the left. Can we do the one on the left all together? Is that okay? Okay. For sure, we're going to have some sort of dichloro group, right? But what is the parent that this thing is attached to? Benzene. Oh, that's so good. Benzene. And so where are the chloro groups here? 1 and 2. 1, 2. So we're going to say 1, 2 dichloro. I kind of ran out of room, but you know what I'm talking about. 1, 2 dichlorobenzene. So what's the only difference between this compound and that compound? So this is 1, 3 dichlorobenzene. All one word, right? No spaces. This is all one word. Are these two compounds, are they aromatic?
Yeah.
Yes. So they are not aliphatic, right? Good. They are mutually exclusive. You are either one or the other, but not both, not neither. Tetrafluoroethene. Okay, what I want you to understand here, how come there are no numbers at the beginning?
Because there's only one place.
There's probably only one combination we can put 4 fluoros on ethene, right? So let's just start at the end. Ethene, what the hell's that? 2 carbons. And what's connecting them? A double bond, right? Ethene is a double bond. And so, okay, let's put, it's saying tetrafluoroethane. We've got 4 fluorines to put. So I'm going to put 1 fluorine here. How many other fluorines can I fit on this carbon? 1 others. And now I'm maxed out, right? Oh, okay. Can you see where this is going? Yeah. So now I can only put 2 on this one, right? We're maxed out. How many hydrogens are on this baby? 0. That's weird. What's the chemical for? This is the structural formula, right? This is the condensed structural diagram. Or this is just the structural diagram. But what is the chemical formula? C2F4. Is this still organic, even though it doesn't have any hydrogens? Yes. It is still organic, right? Because it has a carbon-carbon bond, and anything that has a carbon-carbon bond is typically organic, right? It behaves organically. Okay. This last one, 2,2,5-tribromo 5-methylhexane. Do you want to do that yourself? Yeah, go ahead. And I'm going to walk around and you bug me if you have any questions. You bug me if you don't know what's going on. But this is derived from a hydrocarbon. This is the way we would get this, and we will see this later today. We'll see this, is that you slowly trade out hydrogens for fluorines. Okay. So this used to be C2H4, and then we just slowly popped off a hydrogen and then popped back on a fluorine. And so it's derived from a hydrocarbon.
How do you show that?
Yeah, that is still organic, right? Focus on the things that it can't be, right? Organic compounds.
No, on the board you didn't put ion. I saw that. When you put non-organic, you didn't list ion.
Yeah. On the when we were talking about it like 5 classes ago?
No.
Like at the beginning of today's class?
Yeah.
Yeah, so this is ionic carbonate, right? A carbonate's not. Oh, okay. Yeah. But in order to be a carbonate, you kind of have to be ionic, right?
So if it's ionic,
You can be ionic in organic. Yes. Okay. And so this is organic. It's ionic, but acetate has a C. It's got a methyl group, right?
Yeah.
Yeah. When you take a look at this, that methyl group means that it is organic. It has an organic component.
Okay.
Okay. So focus on it. It can't be a carbon oxide, a carbonate, a cyanide, and a carbide. But it still has to contain carbon, right? It has to contain carbon. Yeah. We'll do both. Is that okay? That's a great question. That's awesome. Okay, let's do this. So, somebody tell me how to start this off. 6 carbons. Okay, and then tell me how else can I do this?
Put a methyl group on 5.
Put a methyl group on 5. A bromo group on 5.
2 more bromo groups on 2 bromo groups.
And then I just fill it in with hydrogens, right? So H3, it's okay if you put it on that side, it's still a methyl group, right? So, yeah, it just looks weird, that's all. And then H2, no H's, H3, right? Okay, let's draw the line diagram of this, just together, just because we can. So 6 carbons, how do you draw line diagrams? 1, 2, 3, 4, 5, 6. The way I would do this is you've got a methyl group coming off of the 5th, and you've got a bromo group coming off of the 5th as well, and then you've got 2 bromo groups coming off of here. So let's prove to ourselves that this is in fact the same picture, right? We should have 6 carbons in a row. 1, 2, 3, 4, 5, 6. Sorry. 1, 2, 3, 4, 5, 6. With a methyl group on the 5th one, a bromo group on the 5th, and 2 bromos on the 2nd. The only things you don't show in a line diagram are carbon-hydrogen bonds. Because if we showed every carbon-hydrogen bond, it would look like a nightmare, right? That's the reason why we don't like structural diagrams, because they look insane. But a bromo group is special, right? It changes the behavior. It's a functional group, so we need to show that in its entirety. Okay, awesome, perfect, that's great. Now we're going to talk about 2 types of reactions. This is a very important type of reaction. It's one of addition, substitution, elimination, polymerization, esterification, and combustion. This is type number 1 of 6. This is our first type of reaction that you have to know. Now, I do want to be very clear. What most of our time that we've spent in organic chemistry, so far most of it's been spent on like naming and drawing. Would you agree with me? But that's because you got to get used to how organic compounds look to begin with. You have to get used to the different ways that we can represent organic compounds. But I want to be very clear. Your diploma exam is much more likely to test types of reactions than naming. So naming's great. You'll probably get 1 naming question. But you might get 5 types of reaction questions. Okay? That much more emphasis should be placed on types of reactions as opposed to naming. I just want to let you know. Okay. Addition reactions involve adding a compound to a double or a triple bond. Because double and triple bonds are super duper reactive, okay, addition reactions are usually quick. Sometimes they can produce two different products. What I want to be very clear about is addition reactions only happen they only occur on unsaturated compounds. Can I add any more atoms to this combination? No, this is saturated, right? As well as, even if I was to draw like a really simple ring like this, this is cyclopropane, right? This is saturated as well, right? There's this, even though it's a ring, and I'm technically missing two hydrogens, right? Because any one of these carbons could be a terminal carbon, we could add more hydrogens. But what I want to say is these are saturated, no double or triple bonds. So I can't add any substances into here. But in a double bonded compound, if I was to take ethene, I can't fit any more unless I break the double bond. Then once I break the double bond, what can I add to both of these carbons? One thing, right? Any one thing. So I could add a Br and a Br, right? Sure, why not? This reaction is extremely fast because double and triple bonds are inherently unstable. They're very high energy bonds. So our first example, you've never seen an addition reaction, and that's totally fine. It's okay. But we're going to start to get used to these. Propene reacts with chlorine gas. What the hell's propene? C3H6. It's alkene, but how many carbons? How many carbons? 3. We're going to use structural and line diagrams and things like that. Okay. So I'm going to use a line diagram. This is propene. It's going to react with chlorine gas. What is chlorine gas? What's the formula for chlorine? Cl2, right? Because it's an element and it's part of Hofbrinkel, then it's diatomic. So this is Cl bonded with Cl, otherwise known as Cl2.
Can we just write Cl2?
Yeah, you can write Cl2, but I want to make sure that you understand you can see it either way, right? I could represent it either way, and you would have to know that. Okay, what's going to happen is this chlorine breaks that double bond. It tears that double bond apart, okay? So all of a sudden, something's missing from the second carbon and something's missing from the first carbon. Do you agree? There's a lack of bonds there. What could we attach to those lack of bonds? We could attach some chlorines. So we still, the propene is turned into propane because we break the double bond. And there's something attached to that second carbon, it's a Cl. And there's something attached to the first carbon, it's a Cl as well. They don't have to be on opposite sides, I'm just conditioned to draw it that way. You could have drawn that chlorine on that first carbon like this. That would have been totally fine. Can we just double check and can we just count our carbons on this molecule? How many carbons are here? 1, 2, 3. At the end of this bond is a chlorine, not another carbon. At the end of this bond is a chlorine, not another carbon. Right? Good. Santana.
So I see that you're foregoing the states of matter. Do those matter?
We forego states of matter because this is a structural diagram. We're trying to show how our structure changes over the course of the reaction.
Right.
But yes, we are foregoing states of matter totally. Okay, so the atoms from that binary compound, they add to the carbons across the double or triple bond. They are never added to the same carbon. With an asterisk. I'm going to talk about why that is here in a second. Does that make sense that one of them has to add to one carbon and one of them has to add to a different carbon, right? When you break that double bond, there's a bond missing on this one and that one, so you can't add both to the same carbon. That doesn't make sense. That's an addition reaction involving the halogens, right? Sorry, I should actually be very explicit. That's involving the halogens. The halogens exist as F2, Cl2, Br2, and I2, right? They all add the exact same way. So we could have, instead of saying Cl2, we could have added I2, and it would have been the iodines that are attaching to the carbons. It's all the same thing. We can get water adding across. So water can also add to a multiple bond, but it's much more difficult and it requires a catalyst to happen. Water can react with ethene in the presence of an acid catalyst. Hopefully this gives you not hopefully, but it might give you PTSD, flashbacks of when we were doing Bronsted-Lowry reactions. What does the word acid mean to you?
Hydrogen.
What? Hydrogen ion, right? H+. It has to mean that to you. Good. Okay, water can react with ethene in the presence of an acid catalyst. So what two things are we reacting together? Nope.
Water.
We're reacting water. And what are we reacting with the water? What are we reacting with the water? Ethene, right? So C. You'll notice I haven't drawn H+ anywhere yet. Where does the catalyst always go?
In the middle. Can you write HOH as H2O?
Yeah. I advise you to write it as HOH, but you can totally write it as H2O. So why? If you were to split water, just like when we split chlorine, it's pretty easy to split chlorine. The Cl pops off the other Cl. So what do you get? You get a Cl and a Cl. Okay, well, if we were to split up water, what are we going to get? An H and an OH. Does that make sense? So what's going to add to the first carbon? When we split up water, water's got to add to these two carbons, right? Which one's going to add to the first carbon? H or OH?
OH.
Sure, OH, sure. I don't know, doesn't matter to me. I want to be very, sorry, I should draw that in a different way, just to make it really explicit. The O is bonded to the H, right? This is what water is, HOH all bonded together. So what was always attached to that first carbon? 2 hydrogens, and we broke the double bond, and what was left? A single bond. So we break the double bond, right? When we add things across the double bond, we break the double bond and we're left with a single bond. Now, if the OH added to the first carbon, what's going to add to the second carbon? Just an H. So this H and this OH, they're from the water, right? So we're still splitting it up and adding it across. Okay, let me be very clear. Did we have to add the OH to the first carbon? No, we could have added it to the second carbon. But it doesn't make a difference because this molecule is so small, okay? We'll come across an example of where that's not the same. Cyclohexene reacts with water in the presence of an acid catalyst. So what I would like you to do is I would like you go ahead and try and write out that reaction.
Are we ever going to be dealing with like base catalysts?
You're going to be dealing with bases, but not base catalysts.
Okay.
Sanjana, typically, I will tell you the catalyst.
Okay.
There's only one reaction where I need you to understand there's a very specific catalyst involved. There's only one reaction. Okay? Yeah. Addition reactions always break the double or triple bond, and it turns it into one less bond. So if we broke a triple bond, what would it turn into? A double bond. If we broke a double bond, it would turn into a single bond, and if we broke a single bond, then it would turn into no bond at all, right? So what's going to attach itself to one of these carbons? The OH. So I don't know, let's say the top one. I could write it like this. I could say bond O, bond H. Often you'll see it written like this. Bond OH. It's implied that the hydrogen is attached to what? The oxygen. Okay, good. And then what got added to the second carbon? A hydrogen. So we don't have to show that in a line diagram, right? You have to show that in either a condensed or a structural diagram, but in a line diagram, I don't have to show it. Hopefully that makes sense. Any questions about that?
So is OH bonded to the first?
The OH is not always bonded to the first one.
First one,
It's-
the start of the double bond?
Sure, the start or the end of the double bond.
Okay.
It could have bonded to this one or that one.
I did a condensed, like I'm doing a condensed structural diagram, and how would I show?
The product.
Yeah.
If you did a condensed structural diagram, so you would, so there's H2, 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 okay? There was always an H attached to this, there was always an H attached to that, but there was a double bond between. So we broke the double bond, and what did we attach to the first carbon?
An OH.
An OH. We broke the double bond, and what did we attach to the second carbon?
Another H. Okay.
Is that okay?
Yeah, that's.
That and that are the exact same thing. You want me to come over there? Okay. Okay. I would like you So just practice this for me, please. Try it out. That's a structural diagram. You can do either. It's totally up to you. Yeah, they're the exact same thing. The O-H and the OH means that H is attached to the O through a bond. It's just that we don't like to draw a lot of the time because relate. That's yes.
If we, like instead of like how you did with the H2, if we drew it and just added that extra symbol, we get it wrong. It's the exact same thing.
But where? Here?
Yeah, like if we just like on like an exam, like if we draw a line and it's the right one.
Because this is a condensed structural diagram, remember carbon hydrogen bonds get condensed down to CH blank. Okay? Now, I probably wouldn't mark it wrong if you went like this. It would just look hella weird to me.
Right. But like,
Okay.
if you do that on just formal exam, like,
There's no written response on the diploma exam. Does that make sense? So they might ask you which of the following is an appropriate structural diagram. They're not going to mix that up. They're either going to put all the hydrogens ballooned out, all the hydrogen bonds, or they're going to put completely condensed. They're not going to make a small mistake like that. They're not going to try and confuse you on little tiny. Oh, I'm going to talk about that. Is that okay? Okay. What does that mean? How many HHs are we attaching?
You just break the.
You broke the triple bond first, and then with the second round of hydrogens being added, then you broke the double bond. Yeah. Yeah, we're gonna do our quiz in 4 minutes. Okay. Does it make sense? When I add the hydrogens across this double bond, the double bond turns into a single bond, so C, 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 C. And then I had my normal hydrogens there all the time. Wow, this is super annoying to draw out already. I'm just completely over structural diagrams. Okay, so let's add our red hydrogens. One goes here, and one goes here. Good? Okay. The next one, when I add the bromine, the triple bond breaks up into a double bond. So the carbon-carbon double bond. It was normally just a hydrogen on each, but now it's like we've added a bromine here. I'll do it in red. We've added our bromine here, and I'll add my bromine there. I'm just conditioned to do it that way. Doesn't matter. You could have done it both on top or both on the bottom, whatever. Now the last one. This is confusing me. Can somebody describe for me what the hell's going on here?
You got it.
Max, thanks for putting up your hand.
I think that there's just like two hydrogens, like so it wouldn't be any different.
There's two hydrogen molecules. So what we're going to do is we're going to add the hydrogen once, and then we're going to add the hydrogen again. Okay? So the triple bond turns into a double bond with the first. You're ahead of me, but it turns into the double bond with the addition of one molecule of hydrogen. Then the double bond turns into a single bond with the addition of the second molecule. Does that make sense? So I'm going to show this in steps. Is that okay? I should have drawn arrows, but whatever. The first product, carbon, carbon, carbon with the double bond. Right? But then we add a second round of hydrogen gas to this, and that second round of hydrogen gas, right, that second round turns the double bond into a single bond. So it just turns into propane, right? Good. We do not have enough time, clearly, to talk about substitution reactions. So we will try our very best to talk about substitution reactions tomorrow. I have all the faith in the world that we can do that.